Yeah, I'm Zefang from the JP Morgan. I would like to introduce our project, the anomaly detection of command shell sessions based on DistilBERT, both supervised and unsupervised model. I would like to thank my manager, John Buford. He's also here. Yeah, here's the introduction part. So this is, I would like to introduce the background of this project. So we want to build interactive command shells, which is like a unique shell sessions people usually use daily, like for your daily job, like type in the command names, try to do something to change the system. So this is quite important things people use daily, and there are many techniques already used by the people to detect anomalies in such command shells, such as the ruler-based method or some machine learning algorithms. But usually such methods use some predefined features or the labels, which are quite expensive in the daily job. We can't get there in the real project. So recently, there are many advantages in the NLP stuff, like broad GPTs, which has a high potential to enhance the security things, which makes them more effectively and adaptive for anomaly detection. So the motivation of this project is try to build a command shell anomaly detections, which can use them automatically to detect anomalies inside the command shell sessions. And although the enterprise can implement rule-based detections, for example, try to define the lots of features, but they are not automatically and use lots of human efforts for this case. So we want to do it automatically here, which can identify the command patterns which are different from other, for majority of the sessions, and automatically assigns the anomaly scores to the sessions, so we can sort them by the anomaly scores. Then the session with higher anomaly scores can be viewed by experts first. So here are three main contributions. One is the first one is that we build a comprehensive anomaly detection framework for in-shell sessions. The second one is we use unsupervised method here. We pre-train a DistilBERT model. And the last one is we build a supervised approach for this one. And we show a pipeline here, maybe a little bit small, but yeah, it's we start from the raw data, we do data pre-processing, and then we have both supervised and unsupervised method. Let me move the second one. Yeah, here's our data. We use a large-scale unlabeled data set from the company, and it includes 90 days data with 15,000 users. It's about 3 million data. But many data are just some data are just empty, and something like data logs, we don't use it. After drop those things, we have 2.4 million sessions here. However, there are a couple of the characters for the data, like there are maze cell prompts and command input and outputs, which means that we can see both input and output inside the command shells. We want only use the command input without the output because they introduce a lot of noise. So after we do the pre-processing, we get about 1 million sessions. And here on the right side, we saw several steps we did for the prompt extraction and command extraction and also data cleaning here. So the idea here is that we build a list of the common commands and also a list of the prompt end. We use the prompt end inside the cell sessions and try to match them with common commands. In that way, we can get the pattern of the prompt. After that, we search the prompt inside the session and get the command lines. And finally, we do some data cleaning here. And yeah, here's the unsupervised method we use. And so here we basically pre-train a DistilBERT model and also train a anomaly detectors based on the embedding from the pre-trained model. So this method was first proposed by the CrowdStrike for the command lines. And for here, we pre-trained the model because the command shell language is very different from the general English. So we cannot use a pre-trained model such as BERT or some other language. And we also can't use something like a pre-trained model for code language like Python code. So that's why we need to pre-train a natural language model here. So we select the DistilBERT model, which is small enough, and we can easily pre-train it on our machine. And the model was pre-trained for the mask language modeling, LLM. And after that, we have pre-trained the model. We extract the embedding from the model. And after that, we use that embedding for the anomaly detector. So as I show here, that we get the pre-trained model, and after that, we get embedding from in sessions, and after we get embedding is the vector, right? And we put a vector inside anomaly detector, and by using anomaly detector, we can get the anomaly score for that stuff. And on the right-hand side, I show two figures for the result of unsupervised method. We can see that the most sessions have a relatively small anomaly scores around 0, which means they are quite normal sessions. But there are some sessions has a higher anomaly scores, which is higher than the 2 or 3. And we think they may have some interesting pattern inside it. And on the bottom right, I have a figure to show all the 4 anomaly detectors. And for here, I have more results for the unsupervised method. And this is to show the anomaly scores versus the number of tokens and the number of command lines inside the session. So usually we can see that the session with more tokens or more command lines, they have a higher anomaly scores, because usually if the session is very long, they can have some a user can do many complicated commands, like not simply something like ls or cd command people usually use. They can do some very rare commands which gives them a higher anomaly score. And on the right hand side, we have a PCA of the sessions with their anomaly scores. The red color means the anomaly score is high. And we can see that the session is pretty clustering together, but there are some sessions on the bottom of this cloud which has a very high anomaly scores. And on the bottom, I have a figure of the command names with anomaly scores. And yeah, most of the common commands, they don't have a much higher anomaly scores, but some of them you can see they have a high anomaly score as too. Yeah, and we have a supervised method here. So the supervised method is basically to fine-tune the DistilBERT model we already pre-trained. We don't have labels, that's we just mentioned before. So in order to use supervised method, we have to generate some labels. We can let some experts to label our data, but since we want to evaluate how the model performs over all data, we have some method to generate many labels. In that case, we basically create a row here. You can see on the one side there the table to show the material techniques and also some suspicious keywords for that techniques. But for here, we only show a partial table. The real table we use is quite long. And we use those suspicious keywords and also material techniques to label the data set. If the data set has more than 3 suspicious keywords, which is something like anomalous commands or some very suspicious file names, we think they are suspicious sessions. But if we have 0, we think they are normal. If we don't have it, we think, okay, that's in between, so we don't use it here. And after we label the data, we can then fine-tune the DistilBERT model. For here, we use a method called setFit. This is sentence transformer fine-tuning, which is basically to fine-tune the data with both normal and all-normal sessions with only a small amount of data. So this is one kind of few-shot fine-tuning method. And finally, we evaluate the method here. So here I can show some results. There's a figure on the right-hand side which to show the average F1 score. We run experiments for 5 times for each point here. And we compare the three method, logistic regression based on the DistilBERT embedding, fine-tune the DistilBERT model directly, and fine-tune the setFit model, which is one efficient way to fine-tune it. And here we show the number of samples per class, which is the number of samples from that class, normal or abnormal. You can see the number is quite small at the beginning, only 16 or 32. They are quite small numbers. They can get a good recall score like 0.8 or 0.9, but the precision is pretty low, like only 0.2. If we increase to about 2,000, which means that we need to label about 4,000 data here. then we can get about 0.88 F1 score. And at the bottom, I saw the techniques and the tactics. Yeah, the names here may be too small to be read, but yeah, it's basically to show the some common techniques, multi-attack techniques show up in the sessions. And yeah, here are some real examples. And I put 3 examples here. The first one on the left is to show the remote command executions for the web server. If you see here, we can see there is a simple HTTP servers. And after that, we saw the user try to kill these servers. And finally, the user we get to transport something, web get to transport something from the server. Yeah, and on the bottom left, we can see there is an example for some potential data exploitation or the credential exposure, which means that they have a username and the credentials in the plain text, which was also detected by the anomaly detector. And on the one side, there is another example which to show the data, disk clean and boot load configuration change. It's around the I think line 5. There is line 5 and 6. You can see there is a disk whisper shell command used and try to clean the command and also change the system configuration here. Yeah, here's the conclusion. So in this project, we build an anomaly detection system for the interactive command shells. We use both supervised and unsupervised method. For the unsupervised method, we basically pre-train the DistilBERT model and use it embedding for the anomaly detectors. And for the supervised method, we fine-tune the DistilBERT model. And finally, we tag the sessions with 2 existing scheme, multi-attack techniques, and suspicious keywords. Yeah, and the pipeline again is here. So here, yeah, thank you.
Questions for our speaker?
Hi, great talk. I would
Thank you.
I would pay like $20 for the whole data set if you have it. You can redact it, but I was wondering if you have what you use to capture the output, or did you not really use the output of the commands?
Oh, we don't use output. We only use command lines.
Okay, all right.
Yeah.
But was that stored in your data that you had to get rid of it then? Or did you just have input?
We use the algorithm to clean those stuff. It is in the data set, but it's too noisy. Like people can type in LS and give a whole file list.
Or interactive commands or whatever. Okay,
yeah.
Cool.
Other questions?
I'm sure JP Morgan Chase would be interested on not a Unix terminal, but a Bloomberg terminal usage, looking for like either insider threat or financial crime, something like that. I don't know if that is one of the extensions that you and your team have thought about.
I'm not quite sure about that. Yeah, sorry.
Well, so of the 15,000 users, how many were true positives on malicious activity?
Finally, it depends on the labeling side. Yeah, we got some examples, maybe tens of examples, like I just showed in the previous slides, like here. Yes, but we don't count for the users. Yeah, for the session numbers, it's probably tens of them are quite interesting anomalies. Yeah.
Have you thought about using an exploit tool to test the malware to get more label data?
Malware tool. I'm not sure if we can use malware tool here. Like usually they use for the commands. Yeah, probably if there are some available tools, yes, we are interesting for the commands, shell commands. Yeah.
Looking at your results, it looked like discovery was the most of your MITRE results. Were you able to look at the results sort of excluding that one category? How did you perform?
You mean for each category, each tech.
Yeah, because when you go into your list of the categories that you came up with, it looked like discovery was
Yeah.
dominating that.
Oh, yes, for here, yes, that's, yeah, you are right. Like, on the left-hand side, we can see I think it's something like a file discovery or the network discovery on so on the table, on the top of the table. Yes, you are right. That is, because those commands are quite common in the sessions, and many people just use it. So that is, I think that we think that we need, basically probably want to filter them out, like to remove those common commands so up in the top techniques, it can improve the model performance. Yeah.
Other questions?
Did you consider a command sequence when you were testing, as opposed to, like, I guess, was this looking in isolation, or were you also grabbing specific sequences or the order of the commands as part of the session as well?
Yes, we use the whole sessions, basically like one token by another token, or the one command name by another command name. So this is a sequence of commands. And yeah, the order of the commands was considered here. Yeah.
Question in the Slack, can you clarify how you labeled which sessions were bad, which I think were used for training the supervised model and also for evaluation?
Yes, it's shown on the table here. Basically, it's we use a threshold. Basically, if the session has many suspicious keywords, like suspicious keywords means the suspicious commands or the file names. For example, like here, the curl or webget or something like best history, those file names are suspicious. So we think they are quite important, and we label those things first. And then if the session has many such suspicious commands was used, I think, okay, this session is an abnormal session here. Yeah, that's the idea.
Other questions? Okay, let's give our speaker a round of applause.